So let's take what we've learned about colligative properties being just based on the number of solute particles. And we have a reliable-ish way to predict the number of solute particles that we expect to see for a solution, given the chemical identity of our solute. Now I'd like to start walking through the different colligative properties that we see, or the effect that this has on different physical properties. And I want to start with vapor pressure. So first and foremost, when we take a pure substance and compare it to a pure substance that has had a solute added and it has become a solution, we see that the vapor pressure of the solution is going to be lower than the vapor pressure of the solvent. So what happens is that solute is really disrupting the equilibrium of the solution of the pure substance and the in the liquid phase and the gas phase. And so as that equilibrium is disrupted by the addition of a solute particle, then the vapor pressure is going to lower as the rate of vaporization is reduced until we hit equilibrium again and our rates of evaporation and our rate of condensation become the same. And when that happens, we'll see that we have fewer particles in the gas phase, which means that our vapor pressure has decreased after it's reestablished equilibrium. Now, this is for a closed system, right? It's different if it's an open system. Those gas particles can kind of indefinitely float away. And what's happening here when we add a solute is nature's tendency to mix is taking over here, and it's driving this lowering of the vapor pressure. And so if we have, and I love this experiment, this like really, or it helps me understand this. So let's take a closed system. We're going to make that system a little bit bigger. And we're going to put two beakers in it. One that is just a pure solvent right here, and one that is a concentrated solution, right? So it's the same solvent, but we've added a solute to it. So the particles that go into the vapor phase can leave the beaker, they can be in this space, but they can't go very far. And what we see over time is that the level of the pure solvent in the beaker decreases as the volume in the solution increases. So it's this entropic driving force for mixing that drives the solvent. Sorry, I'm going to confuse solute and solvent if I'm not careful. So the solvent particles are going to be in the gas phase and also in the liquid phase. And the ones that are in the gas phase, as they crash into the surface of our solution rather than the pure substance, that concentrated solution with the solute particles will want to mix more and dilute that concentration. And so those particles are going to be more easily captured by the solution liquid phase. And so the net effect of this over time is if the rate of condensation has increased, or the rate of evaporation has decreased for our solution, and the rate of evaporation is staying the same and is equal to that of condensation for our pure substance, those gas particles that are coming up into the closed space from the pure substance will actually end up transferring into the liquid phase of our solution, slowly diluting it over time and increasing the volume inside the beaker. And so what we see is as the concentration of solute particles increases, the vapor pressure of the solution is going to decrease. And that's one of our colligative properties. Now we're going to look at this in two ways. When I think of a solvent, I think of something that's probably going to surround something and be volatile. When I think of a solute, my mind kind of goes to two different things. One, it goes to something like an alcohol and water mixture, where both the water and the alcohol are volatile. And it goes to something like a sodium chloride solution in water, where only the solvent is volatile and that the sodium chloride probably wouldn't evaporate. We're going to treat these differently for how we make predictions about vapor pressure in these solutions. And so let's first focus on the situation where we have a solute that is very unlikely to evaporate at all. So we'll call this a non-volatile solute. So what we're going to do to quantify this effect is we're going to use this simple rule called Roult's law. Sorry, difficult to pronounce apparently for me today. And so we can predict the vapor pressure of a solution if we know those concentration of solute particles. So this rule is characterized that we can calculate the pressure of a solution if we know the mole fraction of the solvent, and we multiply it by the vapor pressure of the solvent if it was completely in a pure state. So the pure solvent, and what we're doing is we're basically making a correction, right? We're saying, well, if this is our solvent and it doesn't have any solute particles, we know this would be its vapor pressure. Now we're going to correct that for the presence of solute particles by multiplying it by the mole fraction of the solvent, and that'll give us the actual vapor pressure of the solution. Doesn't matter what that solute particle is at all. It just matters how many moles of particles of the solute and solvent we have. So remember, if I have sodium chloride and I have 1 mole of sodium chloride dissolved in 10 moles of water, each of those formula units of sodium chloride are going to produce 2 solute particles. So I'd really have 2 moles of solute particles. And so my mole fraction would be 0.2 for my, I'm sorry, 0.8 for my solvent rather than 0.9. So asterisk, and we'll do an example. So that's how we're going to calculate the vapor pressure of a solution. And we're going to base that off a correction to the vapor pressure of the pure solvent. We can also calculate just the change in pressure if we want. This is kind of a rearrangement of the equation. If we just want to know, like, how much does the vapor pressure decrease? We really just want to know the change. We can always take the difference between the uh, vapor pressure of the solvent and the vapor pressure of the solution. And to kind of simplify that, what that would equal is the mole fraction of the solute then times the vapor pressure of the solvent. And that'll be how much it's being lowered, which will always be proportional to that mole fraction of solute that was added into the solution, and how that's changed the actual behavior of the solvent is based on those number of particles that we're characterizing in moles.